That is, this forbidden gap is about 1 volt in general, 1 electron volt, very less. So in such materials, what happens is the energy provided by the heat at room temperature is sufficient to lift the electrons from valence band to conduction band. That is, even at room temperature also, the energy provided is sufficient so that the electron can move from valence band to conduction band because of low forbidden gap. Therefore, at room temperature, semiconductors are capable of conduction. Therefore, at room temperature, semiconductors are capable of conduction. But at 0 degree Kelvin, so 0 degree Kelvin or absolute zero, that is minus 273 degrees centigrade. So at 0 degree Kelvin or at absolute zero temperature, all the electrons of semiconductor material are locked in the valence band. Therefore, there is no motion of electrons from valence band to conduction band. Therefore, at 0 degree Kelvin or at absolute zero, the semiconductor material behaves as a perfect insulator. So this is at absolute zero temperature, this is at room temperature. So therefore, at room temperature, semiconductor is capable of conduction, whereas at absolute zero, it behaves as a perfect insulator. One more important point is the forbidden gap depends upon temperature. Forbidden gap depends upon temperature. Generally, the relation for silicon and for germanium is given by the energy gap Eg is equal to 1.21 minus 3.6 into 10 power minus 4 T electron volt. This is for silicon. Similarly, Eg is equal to 0.785 minus 2.23 into 10 power minus 4 T. This is electron volts for, this is for germanium, where T equal to absolute temperature in 0 degree Kelvin. So, with the help of these equations, we can calculate the forbidden energy gap for silicon and germanium. Suppose at room temperature, instead at room temperature means 27 degrees centigrade. So in terms of Kelvin, 27 plus 273, that is 300 Kelvin. So T is equal to 300 Kelvin at room temperature. So just if you substitute a T value for about two equations, Eg is equal to 1.12 electron volts for silicon. Similarly, Eg is equal to 0.72 electron volts for germanium. So this is forbidden gap energy at room temperature for silicon and germanium. So this type of questions are important in the examination. We can expect this type of questions. Suppose if they ask at a particular temperature, then we can directly calculate with the help of these two equations. Similarly, at absolute zero temperature, so that is 0 degree Kelvin. So 0 degree Kelvin means Eg is equal to 1.21 electron volts for silicon. Eg is equal to 0.785 for electron volts for germanium. So this is the forbidden energy gap. For any temperature, we can calculate based on these two equations. Next concept is intrinsic semiconductors. So in semiconductors, we are having two types of semiconductors. One is intrinsic and another one is extrinsic semiconductor. First, we will discuss about what is intrinsic semiconductor. So a semiconductor in its purest form is called intrinsic semiconductor. A semiconductor in its purest form is called intrinsic semiconductor. That is, purest form here means the impurity content. The impurity content in an intrinsic semiconductor is very, very small. So generally, for achieving such a pure form, the semiconductor materials are carefully refined. So one more thing is, to understand the conduction in an intrinsic semiconductor, we will study some particular structure of an intrinsic semiconductor called crystalline structure. So, crystalline structure of intrinsic semiconductor. So how a intrinsic semiconductor will conduct will be explained by this particular concept. We already know that in a silicon, valence shell contains 4 electrons. Similarly, in germanium also, valence shell contains 4 electrons. So these 4 electrons form a bond with the other valence electron of the neighboring atoms. So this is nothing but a sharing of electrons, and such bonds are called covalent bonds. So the atoms align themselves to form a 3-dimensional uniform pattern called a crystal. The atoms align themselves to form a 3-dimensional uniform pattern called a crystal. So here I am showing a 2-dimensional representation of such a crystal. So this is a silicon atom. So this has 4 valence electrons. So this is another silicon atom. It also has 4 valence electrons. So they like this. It is a silicon. So like this, the electrons are shared by other atoms also. This electron is shared by this atom, this electron is shared by this particular atom. So this is called a covalent bond. So this particular, this is a uniform structure. This is a uniform structure, continuous. So which is called a crystalline structure. So both of the electrons are shared by two atoms. So what happens is, so because of this covalent bonds, a single silicon atom has total 8 electrons in its valence shell. These 4 are because of adjacent atoms. So total 8 valence electrons present in the valence shell. So generally 8 valence electrons are allowed in a valence shell. So because of this 8 valence electron, the outermost shell of all the atoms is completely filled. So and the valence electrons are tightly bound to the parent atoms. That means no free electrons are available at absolute zero temperature. No free electrons are available at absolute zero temperature. Therefore, we can say that at absolute zero temperature, intrinsic semiconductor behaves as a perfect insulator. This is very, very important point. At 0 degree Kelvin, intrinsic semiconductor behaves as a perfect insulator. So this is a case at 0 degree Kelvin. Now we will see at some room temperature. So at room temperature what happens? So at room temperature, this is valence band, this is conduction band, this is Faraday band. At room temperature, some thermal energy, the electrons will absorb some thermal energy. So some thermal energy and they break covalent bond, and just they will break covalent bond so that the electrons become free. So here this becomes like this. So this is a free electron. Initially there is electron here. So because of applying thermal energy, all the covalent bonds will break and the electrons will become free. Therefore, at room temperature, the number of valence electrons absorb the thermal energy, due to which they break the covalent bond and drift to the conduction band. Just they will move to conduction band. Such electrons become free to move in the crystal. So when a valence electron drifts from valence to conduction band, breaking a covalent band, a vacancy is created. So here a vacancy is created because the electron is moving to conduction band. Such a vacancy is called hole. Vacancy is called hole. So that is in conduction band we will present electrons will present, and in valence band holes will present. So these are electrons, these are holes. If I apply at thermal energy, if the valence electrons gain some thermal energy, that is at room temperature. That's why at room temperature conduction is possible for a intrinsic semiconductor. So free electrons and holes get generated in pairs always. So this is one pair, this is another pair, this is another pair. So they will get generated in pairs only. The formation of electron hole pair is as shown in figure. So this type of generation of electrons and holes where some thermal energy is taken by the valence electrons is called thermal generation. It's called thermal generation. This is at room temperature. Suppose if we apply some particular energy, so that more number of valence electrons will break covalent bonds, so more number of free electrons will generated. So more conduction is possible. Now we will see recombination of electrons and holes. One important conclusion we made is in an intrinsic semiconductor, conduction of electric current is due to movement of electrons in the conduction band, movement of electrons in the conduction band, and holes in the valence band. Holes in the valence band. That is, so the electrons are like this. Suppose this is a hole. Suppose a electron is moving in this direction. Then what happens? This electron will go to this place. Now, here we will get a hole. Here electron. So nothing but hole is moving in this direction. So electron is moving in this direction, hole is moving in this direction. This is electron, this is hole. So the conventional current direction is in the direction of holes only. So we can say that the electric current is due to both the movement of electrons in the conduction band as well as holes in the valence band. Now one more thing is the movement of these holes and electrons generally random in nature. That is, they will not move in a particular direction. They are random in nature. So what happens is, a free electron approaches a hole. A free electron approaches a hole and falls into it. So this merging of a free electron and a hole is called recombination. Merging of a electron and a hole is called recombination. So because of this recombination, what happens? Number of free carriers reduces. Because of this merging, number of free carriers reduces. And one more point in intrinsic semiconductors is holes and electrons are generated in pairs. So that is both are equal always. Number of holes is equal to number of electrons. So mathematically we can say that n is equal to number of electrons is equal to number of holes is equal to n is equal to p is equal to ni, where n is equal to number of electrons per unit volume, p is equal to number of holes per unit volume, ni is equal to intrinsic concentration. So this is for a intrinsic semiconductor. For intrinsic semiconductor, both electrons and holes are equal.